everybody's with me on that, right? Okay, so that means that since we could have done this thing with any curve, that means that the integral from a to b following any path whatsoever will have the same value. Okay, so this result is a simple conclusion of this result. In other words, the fact that the integral in a closed loop is equal to 0 is equivalent to say that the integral between 2 points, the path integral between 2 points on an open curve is going to be the same regardless of the path. And somebody told me that's a conservative Kornblau, right? That's equivalent to saying that that's a conservative field, which is true, okay? So now we have that the integral between a and b is absolutely independent of the path, okay? You've seen this type of analysis before, a little bit in physics, maybe in math also, okay? But the next statement is the following. So, since the path integral is just a number, right? E dot dl in this case is a scalar quantity, and when you add it up, it becomes just a number, okay? So, for example, if I fix A, just to fix ideas for 1 second, and I vary the point B, meaning I vary the x, y, z coordinates of that point, since the integral doesn't depend on the path, well, in principle, it could depend on the final point. Why not, right? I don't know that if I change the curve, it's going to be still constant. Clear? No? So if I do that, so if I take the point A and I do an integral of this path from here to here, A to B, I get some value. But now let's say that I take this different curve from A to B prime. We don't know that that integral is going to be the same. The only thing that we know is the integral of this path is going to be the same as this one, but we don't know that the value to b is the same as to b prime. That's my point. So then the most general statement that we can make is that the integral will depend on the final point. Yes? And so it will depend on the coordinate of the final point. So this is going to be a certain function of the final point. Okay, so that integral, the integral from a to b of E dot dl is going to be a certain function of that, okay? But now, if I fix the point B, on the other hand, and I vary the point A, and I walk the other way, it could be a function of the point A. It's the same reason. So, but because I'm walking the other way, it's going to be a negative, okay? So in general, the most general statement I can make is that this integral has to be a function of the difference of the 2 points. Okay? Is that clear? Okay. This is just because I cannot say more than that. And so this function f is just an unknown, but if I said something more, I would say, you know, I haven't proved anything. So this is the most general statement. Okay? And so, for example, if I happen to choose to be related with the potential, the electrostatic potential. Okay, we are going to make that connection soon. But out of that new result, so this new result is completely equivalent to this that dl equals to 0, basically. We just argue by talking this. And let's say that out of all the possible curves that I have, I would choose one particular curve, okay? So now that curve from A to B is not necessarily anymore a closed curve. It's just a curve that joins A to B, okay? So let me take a coordinate system x, y, and z, and let's say that I walk from some point x to another point x plus dx, all right? So let's say that this is the point A, and this is the point B, okay? And so what is, if
f of b and f of a is the value of the field at that point?
The value of the field? No. The f is the value of the integral. Whatever it is, I don't know what it is, but it's some, okay, because that, I cannot say more than that because it depends on what electric field I have in my problem. In general, there is going to be some function, I don't know what it is, okay? So we're going to argue this way, and then we are going to see in a different way the same thing. So clear that because of that result, I can choose any curve whatsoever, and I am going to choose a curve that joins the point x, which is my point A, to the point x plus dx, which is my point B. Now they are very, very close together. Okay? We've done this a few times. What is dl for that curve that I just chose? What's that? Dx. Okay, so dl, the vector dl, is dx in the x direction. Okay, so for this curve, we have the dl vector is equal to dx pointing in the x direction, because okay, and the vector electric field is just whatever it happens to be at that location, which is E evaluated at x, y, and z. Okay, okay. So yeah, I don't really need to work necessarily on the y equals 0, z equals 0 in general, you will see. Okay, so when I do these two things, the dot product between E and dl, what do I get? E dot
EX.
Okay.
Which is the function x by z.
Hold on. E what?
X component of E.
Ah, the x component. So E sub x. Okay, E sub x. Very good. So we get the x component of the electric field, which now is a scalar, and itself depends on x, y, and z, like you say. Wonderful. Okay. So when we multiply these two vectors scalarly, we simply pull out the x component of the electric field. Okay? And then the dx, right. Okay. So the next thing I need to do is to do the integral from the point A to the point B of this E dot dl. So it becomes the integral of this thing. Yes? Okay, so what is that? The integral, because the dx is so small, is the integrand. So the integral is actually this. Okay? Yeah, because it's so, huh? No.
Because there's only one dl, so the integral when you're in.
It's just that.
Right, but you just took that function, it's the integral of that.
Yeah? No, because it's a question of semantics, it's a question of what you see. What you do is you take E dot dl and you add it up. Okay? So if I did what you told me, I would have an extra dx. If you tell me that this is the integral of this, then I would have an extra dx. Right? Okay, you are happy with this?
You just define two things. You define E dot dl as Ex dx.
Yeah.
And you define the integral of E dot dl.
But then what would you do? So let's say that is not correct. What is the other interpretation that you have?
You just need to, you were specifying the integral from A to B. You're saying this is infinitesimal.
Exactly. So this is the same thing we've said many times. Look, go back to calculus 1, and I have a function, whatever, g of x dx integrated between a and b, right? Okay, so in general, whatever the integrand of that, that's it. Okay, so now if a is close to b, then you can write this integral as b minus a times g of x times g of a, in fact, whatever, you know. But now, let's say that a is equal to x and b is x plus dx. So then it's exactly what, so nothing, yeah, it's the same thing I'm saying, okay? It's maybe a question of nomenclature. So Joseph, you wanted to say something? Yeah, okay, okay. So another way to see that it works out fine is because if it wasn't like that, even the units wouldn't work. Okay? Sean?
Okay.
Okay, so then the integral for a small interval dx, this is it, and we get this result, that this is equal to f at the point B minus f at the point A. So I'm going to write that result with this thing. So I get the integral is ex at xyz dx equals to f evaluated at the point B, which is x plus dx, minus f evaluated at x. Okay? So I repeat.
You just write the definition of the derivative.
Yeah, I can now, if I move this down, I can use the definition of the derivative. What I obtain is that the x at point xyz is equal to, dividing by dx here, I get f at x plus dx minus f of x divided by dx. That's the derivative of f with respect to x. So it's the derivative of f with respect to x. Okay, so I'm going to stop for 10 seconds in case something is not clear. Okay.
What's the x dl? It's the dx and then the x with the...
So what I was saying is that we proved this result in general.
Yeah.
Okay, and now I'm applying that result for this curve that I chose. It's a straight path that runs from x to x plus dx. So the point A, the beginning of that curve, is x, and the final point is x plus dx. Okay. So that's the meaning of x. So I want to use that result.
Okay, underneath that, it says dl.
Ah, yes, exactly. Yeah. So when you walk on this curve, the element dl is always the step that you take along the curve. Okay? You divide your curve in 100 little pieces. So in this case, it's only one piece because it's already small, and is the length, the segment dx, in the direction of your walk, which is x.
What's the notation of the x with a little triangle? That just means in the direction?
Oh yeah. So it means the unit vector in the direction x, and that's why when I do the electric field, whatever it is, at that location, dot into I get the x component.
Oh, so this whole thing is just saying the x component of the electric field is just the partial derivative?
Yeah, that's what I wanted to get at.
Okay,
Yeah.
I'm a little confused why curve x dx equals f of x plus base minus f of x. We know the integral is a function of whatever distance is between the two, but why doesn't it get a function of is an f the function for electric field, or what is our function?
F is, the meaning of f is that is the value of the integral, whatever that value is. Yeah. I don't know what that is, it's just a function. Yeah. We'll see what that function is, but in general, for now, the argument is that f is nothing but the value of that integral. Also, this statement over here is nothing but the fundamental theorem of calculus, basically. You know, only for a line integral. That's all it is. Okay, so imagine, just to make it simple, that you moved on a straight line, and then you find the integral, the indefinite integral of the integrand, and then you evaluate at the end minus the beginning, which is the fundamental theorem of calculus. Now we are doing that same thing on a curved path. That's the only thing. So, and that function is whatever that integral is. You know, I don't know, but it is the value of that integral. Yeah. And so I'm not saying what that is yet. I'm just saying that it exists. There is some function, whatever. Clear? Okay. So we proved. Look at this interesting thing, that the x component of the electric field can be obtained as the derivative of some function with respect to x, right? Well, so if I chose, and I'm not going to do it, but if I chose a path along the y direction or the z direction, I would have obtained exactly y is equal to df dy, and Ez is df dz, right? Okay, this, if you think for a few seconds, you realize that this is a very powerful result, because it's telling us that a vector of 3 components can be obtained this way. So who cares? No, we can obtain it this way from a single function f. Okay. In compact, wait. True. But don't be that pessimistic. So that means that the electric field, which is a vector at some point, can be obtained as the gradient of a scalar function. And we all know that it's much better to work with scalar functions if possible, because a scalar function is only one number, a function of position, but a vector requires 3 functions at each point, so it's more complex. So if we could actually solve problems using f instead of e, much better. Okay, so fine. What is that mysterious function f? It is related with the electrostatic potential, and actually it turns out that we can actually see that by inspection of Coulomb's law. I'll show you. So we know that the electric field in general is going to have this form. We proved before that we have a bunch of charges I located in 3-dimensional space. Then the electric field E evaluated at the observation point R will have that expression. Okay? So over here we have a function that looks like, okay, this is a vector, of course, but if we ignore for a second, just to try something, the vector form, it is something like 1 over r squared, right? There's an r, so